Hi, my name is Shaheer Khan. This is my presentation, Reading into Simulation, featuring Microsoft Flight Simulator 2020. So a brief overview, Microsoft Flight Simulator 2020 is one of the hottest flight simulators in the market currently. The game has two autopilot systems, a traditional autopilot, which is what a real plane usually features with real-time statistics. And this is what in a traditional sense autopilot would look like. And then there's a new feature in the game called AI control. This utilizes in-game data from the engine to control the plane and try and make decisions that way. One thing users have noted is AI control isn't honestly all that great. Players tend not to use it just because of its low feature usage and just not being very helpful overall. So we're looking today if we can gather data using a vision-based system that could be used for Microsoft Flight Simulator 2020. So going into the project, some raw data that was captured for the project. I captured around 400 photos from different altitude levels. These had 4 categories. We'll talk about that in a second. And this characterized a single runway style. There are multiple runway styles featuring different widths and lengths for runways. However, this single style could be used across multiple runways that have the same style. But in this data set, we chose one runway. There was also proper distance diversification. This is the distance from the runway in a length style, not altitude wide. So there's proper diversification for distance in that sense. First step of the process was runway alignment. Runway alignment was done using key point matching. Key point matching is where two input images that contain the same object at different viewing angles can be aligned using key point matching. A homography matrix is computed and used to align the matrix. And this is done with those key points that I talked about and similarity measures. You can take that homography matrix and align a perspective wrap to get the images together. So what you're seeing here are actually two separate images of the same runway. You can see that there are some points that are aligned correctly. So those would be used in the actual calculation. However, you can see then there are other points that aren't corresponding. What you have to note is that only the runway would be fed into the model instead of all this outside area. So this feature mapping could provide data on how to move the plane to center the runway. This is similar to an ATR algorithm, which stands for automatic target recognition. This is used in the military to accept multiple input images of a target and align them to refine internal parameters to improve the recognition. So this could be used in this sense as the runway being the target and aligning it straight for the plane to land on it. The next step in the process was altitude alignment. What you're seeing here are altitude lights. These are called glide scope lights for the glide slope path. And the glide slope path is the path that the plane takes to properly be aligned with the runway in a height sense, so altitude wise. What the lights you see are white and red. There are 4 of them total, and this corresponds to how high or low you are and if you're on the right path or not. So the more white lights you see or the more red lights you see, say if you're too high or too low, having 2 of each means you're on the right path. So what can we do with these lights? We can take the color of the lights and use this color space to determine if the altitude is correct or not that the plane is on. These glide slope lights use k-means clustering, and determining this relative altitude corresponds with the colors present. So as you can see in this example, there's 2 red and 2 white lights. 50% each means the plane is on the correct path. This uses 3 or 4 clusters to compute the colors. As you can see, green is the primary color in this image. However, green is the color of the grass, and this isn't needed. The reason we go with 4 clusters is because there may be dirt, and this would also be something on a different runway, which wouldn't be in the defined color space. So with that defined color space, we can accurately say, only look at red and white. However, you can see the red tends to go a little pinkish or orangish, depending on the angle of the photo, time of day. So this color space needs to be properly defined so that we can characterize only the lights and not things in the background. One thing to note is the reduced resolution. To be fed into model quickly, this resolution is needed so that the model can quickly compare how much percent of the lights is needed without too much computing. The more computing you do, the more time it's spent, and that time the plane is technically flying. So this needs to be a quick process. So what can we use this altitude colors for? Well, it would be for adjustment input. As you can see, glide slope linearity in the graph present isn't actually perfectly linear. We use trim, which is a feature on the plane where you can make light adjustments to altitude to go up or down more smoothly instead of more jarringly using the yoke. Trim uses a set path with adjustments needed in the form of ticks. So the ticks you trim are certain ticks to go up or down, which you can see in the small photo on the graph. Less or more adjustments are needed at certain points. So you can see at higher points, there is a different tune of adjustment needed than at lower points. This could be fed into the game model, into the game engine from the model, determining how much altitude adjustment is needed to make those lights line up. And this also varies per aircraft, as we use one aircraft. However, different aircrafts have different trim characteristics. So what are some further considerations we can look at with this project? One would be to eliminate user input and automate the process. This would be done using X input controller mapping. X input controller mapping would allow the model to directly interface with the game. However, this requires knowledge of the engine and more points that the model actually provides. So how can we get those points? This would be through further visual components, such as neural networks and object localization. What this could help with is finding those lights specifically in a large screenshot of the entire game or the whole, let's say the whole windshield of the aircraft. Just finding those lights would be done using object localization, and neural networks could more correctly define the altitude as an actual number instead of a category. And this number could show a certain amount of feet or meters that the plane is up in the air using neural networks. So thank you for attending my presentation. This is my contact info if you wish to be in contact with me. Thank you.